Welcome back to this NPTEL online certification course in reactive intermediate and molecular rearrangement. So in the last two classes I was talking about benzyne. So the first class I talk about what are the different methods you can generate benzyne. In the second class I started talking about what are the different reaction. If you form a benzyne, then if you use a diene, then it can participate in a Diels-Hulder reaction. Then there are 3+2 cycle addition. There are some of the 2+2 reactions. So in the today's class we are going to learn some other reactions using benzyne. So we are going to start with the insertion reaction, which is a very important reaction, and you will see several times in the gate and jam you will see question comes from this this particular part. And then we also going to discuss some of the molecular rearrangement. I think some of the rearrangement you have already learned in the previous classes, in case of the carbocation or in the carbanion, but again you are going to see here. Now if you have a benzyne in the reaction, then how this rearrangement going to happen. And then we are going to talk about multi-component reaction. Multi-component reaction means one component will be benzyne, then there will be 2-3 other component going to form a complex product. Okay, so let's start with the insertion reaction. So in the first part of the insertion reaction, there is two different type we can talk about. First, if you see this A and B, so this bond between the A and B has to be weak, so that if one of them A or B could be a nucleophile, then it can attack the benzyne, then it can generate this type of carbon ion here, and now you can see this carbon ion can attack the B followed by cleavage of this A and B. Okay, so what is happening at the end, this part A is coming in this carbon and the part B is coming here. So you are at the end you are making 1,2 disubstituted benzene, correct. So this is a very important method. Okay, and then there is another class, if A and B has a pi bond. Again, if one of them is a nucleophilic, then that can attack. Suppose A is a nucleophile, it can attack to the benzyne, generate these carbon ions here. That carbon can attack to the B. Okay, and then you can see this charge is going back to the A to neutralize the charge on the A, that can generate this type of compounds. Okay, so we are going to discuss each of these different class. So first reaction you can see here. First we are generating benzyne. Again you have this OTF and TMS, the Kobayashi method I have already discussed in the beginning classes. Using a fluoride source, it could be a cesium fluoride, potassium fluoride, you have seen generation of benzyne. Now if you treat with this particular type of compound, where you can see this is a some sort of disulfide compound. If you treat this disulfide compound with a CF3 group here, this SCF3 and SCF3 is coming to this the 1 and 2 position. Okay. Again the mechanistically you have seen what is the mechanism. I think we already talked about this type of mechanism in the previous slide. I am still trying to show you one more time that if you have this SCF3, sulfur is attacking as a nucleophile, then it is generating so what is going to happen in this position now, you can write a positive charge here, there is an anion here. So this can attack to the sulfur, there is a cleavage of the sulfur sulfur bond to give the charge back, and that can end up giving you to this particular product here. Okay. Again if you have diphenyl sulfide, 2 phenyl group here, that can also going to make this particular product. It is going to insert the SPH in the these 2 carbons. So you have a C1 and C2, both will have SPH. Now if you have a scenario here where you have a tributyltene in one side and you have a phenyl on the other side, sorry, you have SPH other side, and again the tene and sulfur bond is the weak bond. So you can see the tributyltene and the SPH will be in these 2 carbon. Okay, so through the cleavage of this bond, as you can see in the mechanism. Then there is another interesting reaction here. We are starting with this anthranilic acid. We have already learned that anthranilic acid, if we use the terbutyl nitride, it will going to generate this corresponding diazonium salt here, the N2 plus, and then you have this COO minus. So it is going to form a Juiter ion. From there it is going to get rid of the N2. So it will be minus N2 and minus CO2. You have learned that it is going to generate this benzyne. And now once the benzene was treated with this particular compound, here you can see the pyridine has nitrogen is nucleophilic. We already know that, so that it can go to attack here, going to generate this carbon ion here. So now this carbon ion is, you can see the nitrogen is already got a positive charge here. So this carbon ion can attack to this carbonyl here. Once it is attacking carbonyl, it will come back making O minus. Finally, it will going to come back, and then what is going to happen? You end up cleaving this. So it's going to come back here. That means you are cleaving this carbon oxygen bond. So at the end, you will forming this type of compound. So that means what is happening? These two parts actually getting chopped here. That means you are chopping here, okay, and this part is getting in this carbon. If you say C1 and C2, then this the rest of the part, this RCO, it could be acetyl or it could be benzoyl, depending on the groups you have, going to go to the C2 carbon. So again, both of these fragments are getting inserted into the benzene ring. Another example here, I think we are starting with not with anthranilic acid, but here you can see there is a XH. It could be a sulfur, NH, or it could be oxygen, and then you have a a benzene source. You have a trimethylsilan and the OTF. In case of cesium fluoride, the cesium fluoride, the F minus going to attack in the silicon, going to generate a carbon ion, is going to get rid of the OTF to form this benzene. From the benzene, what is going to happen? You can see, once you have a cesium carbonate, once you have a cesium fluoride, that can able to abstract this proton from the XH to generate the X minus and cesium plus. Now the X minus going to attack to the benzene to generate, so once the X minus going to attack there, what is going to happen? You are going to generate a negative, so you are going to generate a carbon ion here. So that is going to attack to this ester. Finally, once you are going to attack ester, it will generate this O minus cesium plus and OMe. It is going to get rid of this OMe. It is going to come back and get rid of this OMe to form this type of xanthone or thioxanthone. If you are so if your X equal to oxygen, it is going to be the xanthone. If X equal to sulfur, it is going to be the thioxanthone. Now I am going to talk about this is a very important reaction by Tammer and Stolz group. They have actually developed. So the Stolz group actually started working in this area, starting from this the Kobayashi the benzene compound. So in presence of the cesium fluoride, it is going to generate the benzene. Now you have this beta keto ester. So we have already learned that this proton in between this beta keto ester is highly acidic, correct? So now what is going to happen? This can generate this type of cesium enolate, which is going to come back. This minus going to come back here, going to attack through the carbon, form this carbon ion here. Now that can attack to the it can attack to this corresponding carbonyl group, because there is ester and carbonyl. Carbonyl will be more reactive, so it is going to attack here, form this O minus. Now what is going to happen? It can come back here and cleave this bond between this ring getting back, so it is going to form this minus. Going to form the minus, which will take a proton H plus and going to form the product. Okay. So this chemistry was further used by the Stolz group for the for the synthesis of important natural products. So we are going to try to learn that important key steps, use this methodology. So again, what is happening from there? You can see using the cesium fluoride, you can able to generate a benzene. Now once you generated benzene here, let's try to write the mechanism. And you have this, you can see here you have this beta keto ester. If you see, this is your alpha and beta position. So this is a beta keto, alpha and beta, so beta keto esters. Now what is going to happen? We know that beta keto ester, if you this proton here will be acidic, so this can form a enol here, going to come back and it is going to attack from this position to benzene. Okay, once it is going to attack, it is going to generate So now you see the scenario here, you have the COOET, then you have the CO, and then you have the other phenyl ring which you have a OMe here. So the next thing is going to happen, you have this carbonyl group here. So this negative charge is going to attack here into the carbonyl group, it will form, it will going to come back and finally going to go for a ring expansion. It will generate this minus, so it will generate this product. Okay, you can see once you clip this, now you can see the number of bond will be 1, 2, 3, then it is going to form here the bond 4, 5, 6 and 7. So that is going to form this particular compound, and now once it is going to get a H plus from minus can take H plus to form this particular product. From there, after subsequent step, it can able to synthesize this natural product. We are moving to another set of compound. You have some sort of a amide here. If you have a amide, again you have a nitrogen having the lone pair, so that is going to attack to the benzyne first, generate this type of carbon ion, and you have a nitrogen plus, so that carbon ion is going to attack to this corresponding carbonyl group here, and then going to cleave this carbon nitrogen bond. So through this type of intermediate species is going to cleave this carbon nitrogen bond. At the end, one carbon having the amine, another carbon having the carbonyl. So both these group are getting inserted. Okay. So now if you have this particular compound here, you can see you have some sort of a thiourea. Okay, in that case, what is happening here? Again, once you have a sulfur, the sulfurs are more nucleophilic here, so sulfur going to attack here in this benzyne. So benzyne is forming again through the Kobayashi method using the cesium fluoride. So once the benzyne is formed, it is attacking to the sulfur, generating this carbon ion, and there is a positive charge on the nitrogen. So the carbon is going to attack to this imine. Okay, then it is going to form this type of intermediate species. From there, it is going to cleave this carbon sulfur bond, and then it is going to form. So the one carbon will have the SH, and the another carbon will have this. You can see there will be the carbon nitrogen double bond, some sort of a imine, and there will be a nitrogen here. So now what is going to happen? You can see that you have a SH. So the SH I already told in the previous class that if you have a thiophenol and if you have a benzyne, the sulfur is ready to attack to the benzyne, and then what is going to attack to the benzyne? There will be a H plus which will be taken by the benzyne to form finally this product. Then I am going to talk about the N-acetyl acetamide. So you have a scenario, this is called N-acetyl acetamide. So if you have a N-acetyl acetamide, again from the Kobayashi's method, the benzyne was synthesized, then the benzyne is reacting with this N-acetyl acetamide. Again you can try to draw this resonance structure. You can see there will be O minus here and the N plus. That means now it can come back and it can attack through this nitrogen. Okay, it is attacked through nitrogen, formation of this carbon ion, which is going to attack to this carbonyl group here, then formation of this 4-member intermediate, then cleavage of this carbon nitrogen bond, because this is the bond every case it is getting cleaved. Okay, all the insertion reaction you are seeing, this is the bond which is getting cleaved, and then at the finally it is going to put the acetyl group or the benzyl group in the one carbon, and then this is the amide in the other carbon. Okay. So now we are going to learn about, so we have learned about the insertion reaction. Now we are moving to the several different type of rearrangement which was done using benzyne. We are going to talk about some of the Thaya-Fries rearrangement, then Somlet-Hauser rearrangement, some Claisian rearrangement we are going to talk about, then 2,3 Stevens rearrangement, and also some 2 Smiles rearrangement. I think some of this rearrangement already I have discussed, but now I am going to show you if there is a benzyne how this reaction taking place. So this is a very interesting example. I think this particular research group, what they find out that generally we have learned that if you have this OTF and this TMS, in this scenario if you use a cesium fluoride, it is going to generate a benzyne. But as soon as you have a AX equal to bromo, chloro or nitro, then what they end up finding out, this type of product, and they also got a X-ray crystal structure that confirm that formation of this product. Now we have to find out what is happening here. once you have a X equal to electron withdrawing group, what is happening once the F minus is attacking on the TMS, as I told you, it is generating this corresponding carbon ion. So instead of because you have a X which is stabilizing this anion, now instead of going for a elimination, it is attacking to the sulfur here. It is attacking to the sulfur, and then once it is attacking to the sulfur, it is going to cleave, it is going to attack here and then cleave this sulfur oxygen bond to generate this O minus and this species. Now this O minus going to attack to another benzyne, okay, it's attack to another benzyne, generate this carbon species, which is going to again attack back to the sulfur, okay, and then what is going to happen, it is going to get rid of the CF3 and the SO2 will be coming between this aromatic these two aromatic ring, correct. So that is how they end up making this product. So what is happening from the starting to the product, you can see two different benzyne unit actually kind of reacted together to form this particular compound. Another interesting example here, if you start with allylic amine. So in that case, the nitrogen having the lone pair, it is going to be a nucleophilic, so it is going to attack to the benzyne as is happening here, generating of this carbon ion, and then that carbon ion can take a proton from a solvent to generate some sort of a solvent negative charge. We are going to come back to that. And once it is forming this species, now you can think about that if you give them a numbering as a 1, 2, 3 and then 1, 2, 3. So we have learned this 3-3 sigmatropic shift, correct. We have learned about this Claisen rearrangement. From there, what is going to happen here? You can see there is a this could be aza-Claisen because there is a nitrogen here. So we have learned about this aza-Claisen reaction. So it is going to break this nitrogen carbon bond and at the end form this particular compound. So you can see still benzene is not aromatized, but there is a H here, and if you remember, we have abstracted a proton from the solvent. So that negative part can take this proton and then form the finally going to form this product, okay. Once you form the double bond here, this is going back to a aromatic and you have a amine and you have allyl group in the next carbon. Another interesting reaction here, if you started with a tertiary amine, so this will be a Stevens rearrangement. Now we are going to talk about the Stevens rearrangement and what is happening here. So again the nitrogen having this lone pair, that is going to attack to the benzyne, going to form this this particular intermediate species having this carbon ion. Now this carbon ion is going to find a proton which is going to be acidic. So this will be acidic because it is next to N plus and the electron withdrawing group. So it will form this anion here. So after forming this anion, there is two different things going to happen. At 40 degrees Celsius, one thing going to happen. 80 degrees Celsius, something else is going to happen. At 40 degrees Celsius, let's try to learn what is happening here. So now what is going to happen? This minus going to attack here to this aryl ring. Some sort of ipso substitution going to happen. It is going to attack here. This charge going to go back, and then finally this carbon nitrogen bond going to get cleaved. And that will end up giving you this particular product. You can clearly see that. So what is happening? There is a 1-2 aryl shift. This aryl group now coming from nitrogen to the corresponding carbon, with which the electron withdrawing groups are, and the rest of the things remain same. Okay. Now if you see in the 80 degrees Celsius, what is happening? If you increase the temperature, what is going to happen? Instead of the ipso substitution, it is going to it's readily going to attack in this carbon to cleave this carbon nitrogen bond. Once that is happening, you have a ring expansion going to happen, okay. Instead of the 6 member, now there will be 7 member, okay. So these are the two different situations can happen. In one case, there is a 1-to benzyl migration, or it happens through attacking here and cleaving the bond, or there could be a 1-to aryl migration. So you end up getting both the product in depending on the reaction condition. Then the next example is the Somlet-Hausser rearrangement. Here you can see first in case of the very similar condition of Kobayashi group, you end up generating benzyne. Now the benzyne is going to get attacked with this tertiary amine. Again the nitrogen having the lone pair, that is going to attack here to form this benzylic ammonium salt. If you remember, if you have a benzylic ammonium salt and if there is a carbon ion generation happening, then you remember about the Somlet-Hausser rearrangement. So what is going to happen? We have learned about that in this particular compound, if you look into it, there is this proton next to electron withdrawing group is the acidic proton. So this proton getting abstracted to generate this minus, okay. Now what is going to happen, you can see that there is a 2-3 rearrangement happening. So this negative charge now going to attack here, for this going to come back from this double bond, and there will be cleavage of this carbon nitrogen bond. So once that is happening, you will end up getting to this particular intermediate. The next thing is very simple, this proton is going to get abstracted from here to going back to aromatic compound, that will end up giving to this particular product. We are going to talk about the true smile rearrangement here, how this reaction is happening. So again, you can think about that once you have this amine group here in this sulfonamide, then that nitrogen is going to get attached to the benzyne, going to form this. So it's going to form this carbon ion here, which is going to attack to the attack to the SO2 group. You have learned in this true smile rearrangement. So it's going to attack here, and then it is going to form a carbon ion here, which is going to come back and going to cleave this carbon sulfur bond. Then SO2 is going to get out to get to this corresponding product after the protonation. Now if you have this scenario here, so again this work done by Professor Biju from IIT Bangalore. Here what is going to happen, again this tertiary amine, this nitrogen lone pair going to attach to the benzyne to form this particular intermediate. You have now your nitrogen having plus, and you have a carbon ion, so that can cleave this carbon hydrogen bond because it is next to electron withdrawing group. So this carbon ion going to get generated. Once you have this scenario here, there is a plus and the minus, and you have a allyl group here. It is going to participate in a 2-3 rearrangement. So it is going to attack here and cleave this carbon nitrogen bond to get to the corresponding product. So then I am going to talk about some of the multi-component reaction. So we previously learned that if you have this particular compound, like a carbon fluorine bond, if you use a strong base, then it is going to abstract a minus. So what is happening in this particular lithium which is forming here, in between a fluoride and a methoxy, if you remember, both fluoride and methoxy is a minus I effect. So this lithium going to form first, it is going to end up making this particular benzyne, and then you have to understand there is a organolithium in the reaction. So that lithium is going to attack the benzyne again. Again the question comes, where it is going to get attacked. It is going to attack in this position or this position. We have already learned that the meta attack will be favorable because this anion going to get stabilized through the minus I effect of the OMe group. So that will end up generating you this particular compound. So it will generate a carbon ion here at the beginning. So you will see a carbon ion here, and then there will be OMe, and then you have this another aryl ring with a substitution of fluoro and OMe. What is going to happen? This will going to react with your BOMe whole 3 I's. We are going to talk about this again in the Bourning ester. When I talk about the organoborne chemistry, it is going to form this BOMe whole 2. Okay, it form a Bourning ester. So now if you use H2O to NaOH, you remember the hydroboration oxidation reaction. What is going to happen? The Bourning ester now going to react with the H2O to NaOH to convert to the corresponding phenol. Okay. Another important reaction here, first you treat this compound with a phenyl lithium. Once you treat with phenyl lithium, again there will be proton abstraction from here, that is going to form this corresponding benzyne. You already have a phenyl lithium in the reaction, so it is not going to stay there, it is going to attack here to generate this corresponding lithium. This lithium is ready for a intramolecular 5-exo cyclization. So it is going to take part in the intermolecular cyclization. That lithium finally take a proton to get to the corresponding product. Here what is happening, we started from the corresponding bromobenzene using the magnesium. You can make the corresponding Grignard reagent, and starting from this 1 2 the bromochlorobenzene. Okay, so what is happening, it's a you have a corresponding magnesium, so it is going to form the Grignard. Now you have a chlorine as a leaving group, so it is going to participate in a elimination to form this corresponding benzyne, which will be attacked with this Grignard reagent to form this sort of species. And in place of the copper chloride and this ClPr2, it is going to install the phosphine. So that's how the lot of this Buchwald ligand was synthesized, which was used in a cross coupling reaction. So then the final one, the multi-component reaction here, again from this very similar Kobayashi method, it is generating a corresponding benzyne which is getting attacked by a isocyanate here. Isocyanide, if you remember, the isocyanide always attack through the carbon, not through the corresponding nitrogen, if you remember. So then the isocyanide getting attacking to the corresponding benzyne here. Once it is attacking the benzyne, you can see here it is generating a corresponding carbon ion, and it is generating a nitroleum intermediate, because once it is attacking here, you can see here you are generating this type of nitroleum intermediate here. And now this minus which you are generating here going to take this proton, because this is the acidic proton of the alkyne. So the alkyne will be deprotonated in situ. So once alkyne will be deprotonated, it is going to generate this particular compound in situ, a lithiated alkyne will going to form. Once the lithiated alkyne going to form, what is going to happen? That lithiated species going to attack to the corresponding nitroleum intermediate. So this carbon triple bond N going to get attacked with this organolithium. Okay, once that is happening, you kind of neutralize the charge on the nitrogen to generate this species. Okay, so you can see you have a imine and you have a alkyne here. Now what is going to happen? If you have a proton here in this position, you already have organolithiums, or so you have already base in the present in the reaction. So that is going to abstract this proton, and once this proton going to get abstract, what is going to happen? It is going to form a alene. Okay, so it can take a proton to form this alene. From there, what is going to happen after formation of this alene? What is happening here? Now you can think about that. Now this is going to take part in a reaction with this another alkyne. So it is taking part in a reaction with another alkyne. What is happening here? Again, this is this alkyne electron density coming back here. This is moving here. This double bond is attacking here. Okay, so now it is forming this particular species, and you can think about this. So this particular carbon is attaching here to, at the end what is happening, this is end up forming a pyridine. So in that pyridine, what is happening? There is the 4 carbon coming from here, 1 2 3 4, these 2 carbon coming from this place, and this particular group is actually remaining here, which can finally convert into the corresponding alkyl group. Okay, after this deprotonation, this is getting converted to the corresponding alkyl group. Okay, so that's how you, starting from this type of isocyanide, alkyne and this benzyne precursor, you can able to make this 2 arylated and again the 3 alkylated, and you have, so you have substitution at the 2 3 then 5 6. So you are making a pyridine with so many different substitutions. So this is a very important reaction. So in this particular part, we have learned about different type of insertion reaction using the benzyne. Correct, we have seen several different type of insertion, starting from the disulfide to the beta keto ester and many other variation. Also we have learned some of the molecular rearrangement. Correct, we have seen some of the Claisen rearrangement using benzyne and some of the other rearrangement, and we have always seen if there is a nucleophilic partner, it is going to attack to the benzyne to generate a carbon ion, which is going to attack to the other part. Again, these are the references. Again, I told you that please follow these books which I have given here, the modern alkyne chemistry by Professor Biju, and then some other books. Again, thank you for coming to the class, and I am going to see you guys in the next class.